Why in the 1970s did governments and corporations allow millions of families to serve dinner on plates that emitted radiation directly into their food? This wasn't a secret government experiment. This was just regular business. Picture the scene. A modest American kitchen in 1975. Warm light filtering through macrame curtains. The smell of pot roast settling over a wooden table set with bright orange dinnerware. A mother serves her children from plates the color of California poppies, their glossy surfaces reflecting the overhead lamp. The family sits together, forks scraping ceramic, conversation flowing easily about school and work and weekend plans. Everything about this moment radiates comfort, normalcy, domestic pride in owning matching dishware that cost a week's wages. What none of them know, what none of them can see or smell or taste, is that the very surface holding their dinner is broadcasting atomic decay particles. The cheerful orange glaze protecting their food contains uranium oxide, not trace amounts, not accidental contamination, deliberate, engineered, essential uranium. The same element powering nuclear reactors was baked permanently into millions of kitchen cabinets across the developed world, sitting 18 inches from where children ate their breakfast cereal every morning for decades. The use of uranium in consumer ceramics wasn't an accident, and it certainly wasn't the result of ignorance or corporate recklessness. It was, by the standards of mid-century materials engineering, an elegant solution to a genuinely difficult technical problem. Creating vibrant, permanent color in ceramic glaze is far harder than most people realize. The process demands that pigments survive an environment that would destroy almost any organic compound. Kilns operating above 2000 degrees Fahrenheit, temperatures that vaporize most substances and chemically transform the rest. At these extremes, the glaze itself undergoes vitrification, transforming from a powder coating into a glassy, fused layer bonded at the molecular level to the clay body beneath. Whatever provides color must remain chemically stable throughout this transformation, maintaining its chromatic properties even as the surrounding silicate matrix melts and reforms around it. For centuries, ceramic artists relied on metal oxides to achieve this stability. Cobalt produced blues, chromium yielded greens, iron compounds delivered earth tones. But certain colors remain stubbornly difficult to achieve with consistency and brightness. Reds, oranges, and vivid yellows presented particular challenges. Organic pigments carbonized and vanished. Many metal compounds either oxidized into muddy browns or reacted unpredictably with the glaze chemistry, producing inconsistent results from batch to batch. Uranium oxide solved this problem with remarkable efficiency. When mixed into ceramic glaze formulations at concentrations between 2 and 25% by weight, uranium compounds produced extraordinarily bright yellows, oranges, and reds that remained perfectly stable throughout the firing process. The colors were clean, saturated, and most importantly, permanent. They wouldn't fade under ultraviolet light. They wouldn't degrade when exposed to repeated thermal cycling from dishwasher to oven. They wouldn't leach away from normal food contact or alkaline detergents. For manufacturers competing in an increasingly crowded housewares market during the post-war consumer boom, uranium-glazed ceramics represented a significant competitive advantage. The colors simply looked better than anything achieved through alternative methods, and they stayed looking better year after year. The practice dated back to the 1830s, when European pottery works first experimented with uranium as a colorant. By the late 19th century, uranium glazes had become relatively common in decorative ceramics, though their use remained limited by the modest availability of uranium ore and its expense relative to other pigments. The First World War changed nothing about this practice. Neither did the discovery of radioactivity itself. Even as scientists like Marie Curie died from radiation exposure in their laboratories, the decorative use of uranium in consumer goods continued uninterrupted through the 1920s and 1930s, constrained only by economic factors and fashion trends. Then came the Manhattan Project. In 1942, The United States government seized control of all domestic uranium supplies for military purposes. Manufacturers who had been using uranium oxide in glazes, glass colorants, and other industrial applications suddenly found their supply chains severed. The Atomic Energy Commission, established in 1946 to oversee nuclear technology in the post-war period, maintained strict controls over uranium distribution. For nearly a decade, uranium-glazed ceramics essentially vanished from production lines. But the Manhattan Project and subsequent nuclear weapons programs created an unexpected byproduct: massive quantities of depleted uranium. The enrichment process used to concentrate fissile uranium, 235 for bombs, necessarily left behind vast stockpiles of uranium. 238, the more common isotope with less immediate military utility. This depleted uranium retained roughly 60% of natural uranium's radioactivity, still emitting alpha particles through decay processes, but it was no longer useful for nuclear weapons or reactor fuel. By the mid-1950s, the government faced a storage and disposal problem. Enormous quantities of radioactive material sat in facilities with no clear purpose, representing both a security concern and a waste management challenge. The solution was bureaucratic and economically rational: release the depleted uranium back into civilian markets. Starting in the mid-1950s and accelerating through the 1960s, the Atomic Energy Commission made depleted uranium available for industrial purchase. Manufacturers could acquire uranium oxide for ceramic glaze production at prices far below what uranium ore had cost in the pre-war era. The government was essentially paying to offload radioactive surplus by making it artificially cheap for civilian use. Ceramic factories embraced the opportunity. The post-war housing boom had created unprecedented demand for housewares. Millions of new suburban homes needed to be furnished, and manufacturers competed intensely for market share. The ability to produce brilliant, fade-proof colors at low cost represented exactly the kind of product differentiation that could move inventory. Through the late 1950s, 1960s, and into the 1970s, uranium-glazed dinnerware returned to full production. The bright oranges and reds became style signatures of entire product lines, marketed as modern, durable, and distinctively American. Trade publications from the period describe the colors in enthusiastic terms, emphasizing their permanence and visual appeal, without mentioning the radioactive content that made those properties possible. Nobody was hiding the uranium. Manufacturers didn't conceal what they were doing. The information simply wasn't relevant to consumers, and in the regulatory environment of the time, there was no requirement to disclose it. The prevailing assumption, both within industry and among government regulators, was that ceramic glaze formed a stable matrix that would contain the uranium indefinitely. The radioactivity was sealed away, inert, presenting no meaningful exposure pathway. The plates were safe because the uranium was locked inside glass. This assumption was wrong. Understanding why uranium-glazed dinnerware posed a genuine health risk requires distinguishing between two fundamentally different exposure scenarios. The physics of radioactive decay doesn't change based on how humans interact with radioactive objects, but the biological consequences change dramatically. A uranium-glazed plate sitting unused on a shelf does emit radiation continuously. Uranium-238, the primary isotope in both natural and depleted uranium, has a half-life of approximately 4.5 billion years, meaning it decays extraordinarily slowly by human timescales. But slowly doesn't mean never. At any given moment, uranium atoms within the glaze are undergoing spontaneous decay, ejecting alpha particles as their nuclei shed excess energy and transform into thorium-234. Alpha particles are helium nuclei, 2 protons and 2 neutrons bound together, stripped of electrons, carrying a positive charge. They're expelled from decaying uranium atoms at speeds approaching 5% of light speed, carrying substantial kinetic energy. But despite this initial velocity, alpha particles interact intensely with matter. Their relatively large mass and positive charge means they collide frequently with atoms they encounter, transferring energy and losing momentum with each interaction. In air, alpha particles travel only a few centimeters before stopping completely. A sheet of paper blocks them. Clothing blocks them. The dead outer layer of human skin, composed of keratinized cells containing no living tissue, blocks them completely. This shielding effect means that a uranium-glazed plate sitting across the room poses essentially no radiation exposure to a person. The alpha particles can't reach living tissue through air and clothing. Beta particles, which some uranium decay products also emit, travel slightly farther but are still easily stopped by minimal shielding. Even gamma radiation, the most penetrating form emitted by uranium decay chains, exists at relatively low energy levels from depleted uranium and contributes minimal dose at typical household distances. From a radiation safety perspective, owning uranium-glazed dinnerware and storing it in cabinets represented negligible risk. If the plates had remained permanently unused, sealed behind cupboard doors as decorative heirlooms, the story would end here. The uranium would have remained locked in the glaze matrix, its radiation absorbed harmlessly by air and wood, presenting no meaningful pathway to human tissue. But dinnerware doesn't remain unused. The entire purpose of plates and bowls and mugs is daily, repeated, intimate contact with food and liquids at elevated temperatures. And that's where the engineering assumptions about glaze stability began to fail. The critical distinction is this. External radiation exposure to intact uranium objects poses minimal danger because the radiation can't penetrate to living tissue. Internal radiation exposure from ingested or inhaled radioactive material represents an entirely different category of hazard. When alpha-emitting isotopes enter the body and become lodged in tissues, the short range that makes them harmless externally becomes precisely what makes them devastating internally. An alpha particle emitted from uranium embedded in soft tissue doesn't travel far, but it doesn't need to. It deposits all of its substantial kinetic energy into the immediately surrounding cells, causing dense ionization damage to DNA, proteins, and cellular membranes. A single alpha track through a cell nucleus can shatter DNA in multiple locations, creating complex, difficult-to-repair breaks that frequently lead to cell death or mutation. The question then isn't whether uranium-glazed plates were radioactive. They obviously were by design. The question is whether the uranium remained contained within the glaze under conditions of normal use, or whether it escaped into food and was consumed by families eating from those plates over years and decades. The answer is that it escaped, not immediately, not obviously, but progressively and inevitably through two distinct mechanisms. Ceramic glaze is not, despite appearances, an impermeable seal. It's a complex silicate glass, riddled at the microscopic level with defects, variations in composition, and vulnerabilities to both mechanical and chemical degradation. Under laboratory conditions with virgin glaze surfaces, uranium release can indeed be minimal or undetectable over short time periods. But dinnerware doesn't exist under laboratory conditions. It exists in kitchens, subjected to mechanical stresses and chemical exposures that accumulate over thousands of cycles of use. The first failure mechanism was mechanical. Every time someone cut food on a uranium-glazed plate with a steel knife or fork, they created microscopic abrasions in the glaze surface. Stainless steel has a Mohs hardness of approximately 5.5. Ceramic glaze ranges from 5 to 7 depending on formulation, meaning knife edges can and do scratch the surface, especially when force is applied through cutting motions. These scratches aren't necessarily visible to the naked eye, particularly in the early stages of use, but at microscopic magnification, heavily used plates show networks of fine fractures, scratches, and chips that penetrate through the glaze layer, exposing the uranium-bearing glass matrix to direct contact with food. Once the glaze surface is compromised, uranium becomes available for physical removal. Any abrasive contact generates fine particles of glaze material containing uranium oxide. These particles mix with food residue, get redistributed by liquids, and are consumed along with the meal. The particle size is small enough to be effectively invisible, but large enough to contain numerous uranium atoms. When swallowed, These microscopic shards pass through the digestive system. Most transit completely and are excreted, but some fraction dissolves in stomach acid or intestinal fluids, releasing uranium ions into the bloodstream. From there, uranium preferentially accumulates in kidneys and bone tissue, where it remains for extended periods, continuously emitting alpha radiation into surrounding cells. The second failure mechanism was chemical leaching, and this pathway proved both more insidious and more difficult to predict. Ceramic glaze is chemically stable under neutral conditions, but many common foods are decidedly non-neutral. Tomatoes have a pH around 4.3 to 4.9. Citrus fruits range from 2.0 to 4.0. Vinegar-based salad dressings sit around 2.5 to 3.5. Coffee is approximately 4.8 to 5.1. These acidic liquids, especially when hot, react with the silicate matrix of ceramic glaze through a process called ion exchange. Silicon-oxygen bonds in glass are vulnerable to attack by hydrogen ions in acidic solutions. The acid essentially dissolves the glaze at extremely slow rates, breaking down the silicate network and releasing whatever metal ions are embedded within it. For uranium-glazed ceramics, this means that uranium ions can leach directly into acidic food without any mechanical damage to the glaze surface. The process accelerates with temperature. Hot coffee leaches more uranium than cold coffee. Hot tomato sauce leaches more than cold tomato sauce. The combination of acidity, heat, and extended contact time created optimal conditions for extracting uranium from glaze into food. Studies conducted in the late 1970s and early 1980s, after concerns about uranium dinnerware finally prompted systematic testing, found measurable uranium migration under simulated use conditions. When uranium-glazed ceramics were tested with acetic acid solutions at elevated temperatures, uranium concentrations in the liquid exceeded background levels by factors ranging from 10 to several hundred, depending on glaze formulation and condition. Plates that had been used heavily for years showed significantly higher leaching rates than new plates, confirming that mechanical damage enhanced chemical extraction. The biological fate of ingested uranium depends on its chemical form, but uranium entering the body through food generally behaves as a heavy metal toxin with radiological properties. Soluble uranium compounds are absorbed from the gastrointestinal tract at rates of 1 to 5%, with the absorbed fraction entering the bloodstream and distributing primarily to kidneys and skeleton. The kidneys attempt to filter uranium from blood, but in doing so, concentrate it in renal tubules where it can cause both chemical toxicity and radiation damage. Uranium is nephrotoxic, meaning it damages kidney cells through direct chemical interaction independent of radioactivity. But uranium is also radioactive, and uranium that lodges in kidney tissue continues emitting alpha particles for years, creating localized zones of intense radiation exposure. In bone, uranium substitutes for calcium in the mineral matrix, becoming physically incorporated into skeletal structure. There it remains, with a biological half-life measured in years, continuously irradiating bone marrow and adjacent tissues. Bone marrow is particularly radiation sensitive because it contains stem cells constantly dividing to produce blood cells. Chronic alpha radiation exposure to marrow increases risk of leukemia and other hematopoietic cancers through accumulated DNA damage in these stem cell populations. The dose calculations are complex because they depend on intake rates, which varied enormously depending on individual use patterns, glaze condition, and food choices. A family that rarely used their uranium-glazed plates, or used them only for dry foods, accumulated minimal exposure. A family that used the same plates daily for acidic foods, cutting directly on the surface with knives, accumulated substantially more. There was no uniform exposure scenario, which made epidemiological tracking nearly impossible. But the physics was clear. Uranium was escaping from glazes into food, entering human bodies, and delivering internal radiation doses that external radiation from intact plates could never produce. Nobody was monitoring this. Nobody was measuring individual exposure. The practice continued for decades without systematic health surveillance because the assumption that glazes contained their uranium safely remained unchallenged by regulatory agencies. The gap between scientific understanding of radiation hazards and implementation of consumer protection regulations represents one of the more troubling aspects of this history. It wasn't that scientists didn't know alpha-emitting isotopes were dangerous when ingested. Marie Curie died in 1934 from aplastic anemia caused by radiation exposure. Radium dial painters, who ingested radium-226 by licking paintbrushes, developed catastrophic bone cancers and jaw necrosis by the 1920s. The biological dangers of internal alpha emitters were well established in occupational health literature decades before uranium-glazed dinnerware reached peak production. But scientific knowledge in specialized journals doesn't automatically translate into consumer product regulation. The institutional infrastructure for systematic consumer protection barely existed until the second half of the 20th century. The United States Food and Drug Administration gained authority over food safety progressively through legislation in 1906, 1938, and subsequent amendments, but its early focus remained on preventing acute poisoning and obvious contamination, not chronic low-level exposure to radioactive materials in housewares. Uranium-glazed dinnerware occupied a regulatory blind spot. It wasn't food, so food contamination regulations didn't directly apply. It wasn't a radiation source in the sense of industrial or medical equipment. So radiation safety regulations focused on nuclear facilities and X-ray machines didn't apply either. It was a consumer product that happened to contain radioactive material and happened to contact food. But no specific regulatory framework addressed this intersection until concerns emerged from unexpected directions. The shift began in the 1970s, driven partly by broader environmental and consumer safety movements, and partly by advances in analytical chemistry that made low-level contamination measurable. Atomic absorption spectroscopy and neutron activation analysis allowed researchers to detect heavy metals in food at parts per million and parts per billion concentrations. When these techniques were applied to studying lead migration from ceramic glazes, a major consumer safety issue already under investigation, some researchers expanded their analyses to include other heavy metals, including uranium. What they found was inconsistent but concerning. Some uranium-glazed ceramics released essentially no detectable uranium under standard test conditions. Others, particularly older or heavily worn pieces, released uranium at levels that raised questions about cumulative exposure over years of daily use. The data wasn't dramatic enough to trigger immediate recalls or emergency warnings, but it was sufficient to prompt regulatory attention. In 1971, the FDA issued informal guidance to ceramic manufacturers regarding heavy metal release from glazes. Though these initial recommendations focused primarily on lead and cadmium, uranium wasn't specifically addressed in early versions of these guidelines. By the late 1970s, as testing expanded and public awareness of radiation hazards grew in the aftermath of 3 Mile Island and increasing coverage of nuclear waste issues, pressure mounted for explicit limits on radioactive materials in consumer goods. Different countries approached the problem at different speeds. Some European regulatory agencies moved faster than their American counterparts, implementing restrictions on uranium in ceramics by the mid-1970s. The United States Food and Drug Administration eventually established specific limits for uranium release from ceramic foodware, measured in micrograms of uranium per liter of extracting solution under standardized test conditions. These limits were set conservatively, designed to ensure that even daily use over a lifetime would not result in uranium intake exceeding established safety thresholds. Manufacturers responded by reformulating glazes. Alternative pigments that could approximate the bright oranges and reds without uranium had been under development throughout the 1970s, though they generally cost more and didn't quite match the intensity and permanence of uranium-based colors. But as regulatory pressure increased and liability concerns mounted, the cost differential became irrelevant. By the early 1980s, major ceramic manufacturers had largely phased out uranium oxide from new production, transitioning to rare earth oxides, cadmium-selenium compounds, and other colorants that could pass heavy metal release testing. The transition was quiet. There were no massive recalls of existing uranium-glazed dinnerware from consumer homes. No public health campaigns urged families to dispose of their orange plates. The regulatory approach focused on preventing new production rather than remediating past exposure. This was partly practical. Identifying and recovering millions of individual plates from households would have been logistically impossible, but it also reflected uncertainty about the actual magnitude of health risk. While the potential for uranium ingestion was clear, establishing definitive epidemiological links between uranium dinnerware and specific health outcomes in the general population was enormously difficult given the long latency periods for radiation-induced cancers and the impossibility of reconstructing individual exposure histories decades after the fact. Some academic researchers attempted retrospective studies, trying to correlate uranium dinnerware use with cancer rates in specific populations, but these efforts faced insurmountable methodological challenges. Too many confounding variables existed, too much time had passed. Exposure varied too widely. The studies that were published generally concluded that while uranium-glazed dinnerware represented a theoretically unnecessary radiation exposure that could have been avoided through better regulatory oversight, proving direct causation of specific health outcomes in exposed populations was not feasible with available data. This inconclusiveness allowed the issue to fade from public attention rather than escalating into major scandal. Unlike lead paint or asbestos, which generated clear epidemiological signals and massive litigation, uranium dinnerware became a footnote, a cautionary example discussed in materials engineering courses and radiation safety seminars, but not a cultural reference point like other toxic exposure histories. Yet the absence of definitive proof of widespread harm doesn't erase the fundamental failure. For decades, millions of families unknowingly ate from radioactive plates because the people designing, manufacturing, and regulating consumer products didn't ask basic questions about long-term exposure pathways. The system assumed containment without testing whether containment persisted under real-world use. It assumed that what worked in theory, uranium locked safely in glass, would work in practice, even when subjected to years of mechanical abrasion and chemical attack. These assumptions were wrong, and the error continued not because evidence was unavailable, but because nobody with authority was looking. There's a particular discomfort in contemplating objects that should be benign but aren't. A plate is supposed to be one of humanity's most fundamental technologies, refined across millennia to perform a simple function: hold food. The engineering involved in modern ceramic dinnerware is sophisticated, certainly, but the end product is meant to be transparent in use. Invisible infrastructure that facilitates eating without inserting itself into consciousness. We don't think about plates. We shouldn't have to. Uranium-glazed dinnerware violated this expectation by introducing invisible complexity with invisible consequences. The plates looked normal. They felt normal. They performed their intended function perfectly well, perhaps better than alternatives given their exceptional durability and color retention. Nothing in the user experience suggested danger. No warning label indicated radioactive content. No educational campaign taught consumers to recognize uranium-glazed ceramics or understand what their use implied. The technology operated silently, asking nothing of its users except routine interaction that happened to include ingesting microscopic quantities of alpha-emitting heavy metals. This is perhaps what makes the story most unsettling. Nobody acted with malice. Manufacturers weren't trying to poison customers. They were trying to produce superior products that would sell in competitive markets. Regulators weren't ignoring known hazards. They were operating within frameworks that hadn't yet caught up to understanding how radioactive materials could pose risks outside of obvious industrial and medical contexts. Consumers weren't making reckless choices. They were buying attractive dinnerware from reputable retailers with no reason to suspect anything unusual about the bright colors on their tables. The failure was systemic and structural, rooted in the gap between what we could make and what we understood about what we made. The capability to incorporate uranium into consumer goods arrived decades before the regulatory infrastructure to evaluate whether doing so was advisable. Market incentives favored distinctive, durable products. Engineering incentives favored materials that solved technical problems elegantly. Uranium oxide checked both boxes beautifully. What it also did, introduce a persistent low-level internal radiation exposure pathway into daily domestic life, wasn't invisible because it was hidden, but because the systems for making such things visible didn't exist yet. We have, slowly and imperfectly, built those systems. Contemporary materials regulation in developed nations now includes explicit consideration of heavy metal migration, radiation exposure, and long-term degradation of consumer products. New materials undergo testing that simulates years of real-world use before reaching markets. When hazards are identified, even retrospectively, mechanisms exist for public notification and product removal. The regulatory apparatus is far from perfect and remains vulnerable to corporate pressure and political interference, but it is substantially more comprehensive than what existed when uranium oxide was being mixed into ceramic glazes by the ton. Yet new gaps undoubtedly exist. We are surrounded by complex materials and technologies whose long-term interactions with human biology remain poorly understood. Microplastics are accumulating in human tissues in ways we're only beginning to characterize. Perc and polyfluoroalkyl substances persist in environments and bodies with half-lives measured in years. Nanoparticles in consumer products have surface chemistry and cellular uptake pathways that don't scale predictably from bulk material behavior. We're very good at making new things. We're substantially worse at predicting what those things will do over decades of environmental and physiological exposure. The uranium dinnerware episode offers an uncomfortably clear case study in how this pattern operates. Take a material with useful properties, engineer it into consumer products. Distribute those products widely. Assume the engineering contains the hazard. Discover later, sometimes much later, that the assumption was wrong. By the time the error becomes clear, exposure has already occurred. Remediation becomes impossible. All that remains is attempting to prevent repetition with the next material, the next product, the next assumption. Somewhere, in homes and estate sales and antique stores, uranium-glazed plates still exist. They're collectible now, valued precisely because they're no longer made. They're bright colors and distinctive style markers of a particular era. People display them, sometimes use them, mostly without knowing what makes those colors so permanent. The uranium is still there, still decaying, still emitting alpha particles into whatever space surrounds the glaze. If the plates remain intact and unused, they pose negligible risk. If someone cuts food on them, serves acidic sauce, runs them through thousands of dishwasher cycles, the uranium will do what it has always done: slowly escape into whatever touches it. The half-life of uranium-238 is 4.5 billion years. The plates will remain radioactive long after every person who designed them, manufactured them, sold them, bought them, ate from them, and worried about them is gone. The engineering solution was permanent. The consequences are permanent. What we learned too slowly to matter for the people who needed the information most. That gap between creation and comprehension is still with us. It's the persistent remainder in the equation of technological progress, the variable we consistently underestimate until the data forces recognition. The plates glow under ultraviolet light, a ghostly green fluorescence from uranium compounds that made them so desirable in the first place. It's beautiful, in a sterile sort of way, beautiful and toxic, impressive and dangerous, an achievement in material science that also represents a failure in systems thinking. That duality doesn't resolve. It just sits there, inert and radioactive, waiting to be rediscovered by each generation that has to learn again that making something doesn't mean understanding it, and understanding it doesn't guarantee we'll act on that understanding before damage is done. We served dinner on radioactive plates for decades because we could, because it solved problems we cared about, and because the problems it created were invisible until we developed the tools and frameworks to see them. The question isn't whether we've stopped doing this. The question is what we're doing now, that future researchers will look back on with the same clinical bewilderment, wondering how we could have been so sophisticated in our engineering and so blind to its consequences.